Welcome to this series of introductory lessons related to the time value of money. My name is Brent Pritchard. I teach college finance courses, and I'm here to help you grasp this all-important concept. This introductory series is designed to help you learn how to apply the mathematics of finance in less than a month, provided you commit to one or more lessons a day. It's that easy. Acquiring the hard skill that is the mathematics of finance does not need to be hard. I hope you enjoy this fun new take on this age-old concept. And after you've done that, please consider telling your friends about this channel, TVM Rules, and the book, Would Your Boomerang Return, also known as the Boomerang Book, that made it possible. I like to start every class with a quote. So here we go with a quote of the lesson. It comes from Henry David Thoreau. I make myself rich by making my wants few. The focus of this lesson is the present value of an ordinary perpetuity. A perpetuity is an annuity on steroids. An annuity, as you may remember, is made up of frequent payments. Now that we're introducing the perpetuity, I think it's worth discussing the difference between an even perpetuity and an uneven perpetuity, as I see it. Amount and timing is the giveaway, but there's also a nuance. When I hear the word even, I think equal. An even perpetuity is a kind of even annuity with perpetual timing. When the payments in the series are not even or equal, then I think we're dealing with an uneven annuity, which might have payments that increase based on the growth rate of inflation, for example. But there's a difference between a constant growth rate of, say, 5% with respect to the PMT payment and what I call even. In my book, this is an uneven perpetuity. Now, in this slide, notice how the OP for ordinary perpetuity is in parentheses. Why is this? Because it's calculated using the PV key on your financial calculator. This notation relates to the third window of the TVM wallet, as we'll see when we work through the real-world example for this lesson. We've discussed that you might encounter a perpetuity that has a PMT payment that increases based on a certain growth rate, maybe the inflation rate. This is factored in by way of the variable G in the denominator of the building block present value of an ordinary perpetuity equation. We'll work through examples with and without a growth rate of inflation in a few. Similar to the present value of an ordinary annuity, the present value of an ordinary perpetuity is as of one period before the first payment in the series. Here's the real-world situation we'll be analyzing for this lesson. Let me turn on the tablet and we'll get ready to go here. Make sure the pen's all inked up and ready. Good, we got our blue ink in it. So a friend wants to establish an endowment. And that's the real world situation that we're dealing with here. We're told to assume a true annual investment yield of 4%. And this endowment is going to go to fund higher educational opportunities. And this is an annual distribution that will start 1 year from today. So let's draw the TVM wallet. That's the first thing that we want to do. So we've got our three windows. First thing I'm going to do is write in the 5 primary time value of money inputs, the keys on your financial calculator that you'll be using more often than not. That's the abridged symbol. We were told that the true annual investment yield is 4%. So that's what we're modeling. So let's fill in the blank. How are we telling time? Well, let's work through the 3-1-2 warm-up routine. And this also relates to the different windows, the 3 windows in the TVM wallet. What's the 3 stand for? Well, time value of money. 1, 2, 3. So let's start in the third window. We're talking about money. We've got PV, PMT payment, and FV. So how are we counting money? Well, in this real world situation, we're told that the annual distribution from the endowment will be $50,000. So that's how we're counting money. We can take it a step further and say that's an annuity on steroids, because the whole idea is that that annual distribution will happen in perpetuity. There's no FV, there's no single lump sum payment anytime in the future that we need to analyze. And we're solving for the present value of an ordinary perpetuity. So we put OP in parentheses because we can. How are we telling time? Okay, so we counted money, $50,000, and we called it by name. It's a perpetuity, so an annuity on steroids. We counted the money. That's the third window of the TVM wallet. Now we move to the first window of the TVM wallet. How are we telling time? We're being told how to tell time in this case, so we don't have the flexibility to choose. There's an annual time span between the period markers on the timeline. So we'll put an A here for the subscript for uppercase N so that we can remember how we're telling time. Again, only a true annual investment yield is going to work. And that's great because we were told that the true annual investment yield is 4%. Now, I need to input that as a percentage in my trusty HP12C. Maybe your financial calculator is different. And this is a great time to remind you that the TVM wallet is meant to be used in conjunction with your financial calculator. So let's keep visualizing. $50,000, that's the first distribution that's going to happen 1 year from now. And here we have a little lazy 8. That's the symbol for infinity. That's one of the things that I wanted to point out on this slide. Here's the next thing that I wanted to point out. When you're dealing with a perpetuity, here we're solving for the present value of an ordinary perpetuity, so we're going to circle that. We can input 9999 for uppercase N. When we solve for the present value of this ordinary perpetuity, we get negative $1,250,000. So how do we interpret the negative sign? Remember, signs matter. That's the amount that would be required to fund this endowment. There's a negative sign, so that's a deposit that would need to be made. That's an investment that would need to be made. So there we go. That's the present value of this ordinary perpetuity. Let's move on to the double check. Obviously, we're going to use the building block present value of an ordinary perpetuity. Remember that a perpetuity is nothing more than an annuity on steroids. And here's how we write the building block present value of an ordinary perpetuity equation. In the denominator, notice that the true investment yield is underlined. I think that's a simple way to do it. And that stands for I minus G. In other words, the true investment yield minus the growth rate if a growth rate is applicable. And there's not a growth rate here. Remember, that's an even payment. Those payments are all equal. We're talking about the $50,000 annual distribution. So let's work this down. The present value of an ordinary perpetuity equals the $50,000 payment over I underlined, which in this case is 4%. So we need to write this as a decimal form. And when we solve for the present value of an ordinary perpetuity, we get $1,250,000. I'm going to circle it. Notice there's no negative sign here. Whenever we're working with building block time value of money equations, you're going to see minus signs but you're not going to see any negative signs associated with PV, FV, or the PMT payment. So let's move on to the next real-world example that is very close to the one we just worked out. There's just one slight change, and the slight change here is that the annual distribution is going to be growing at a constant rate. So again, this is what I consider to be an uneven perpetuity, because there's nothing even or equal about the PMT payment. We've got a constant growth rate here. And notice the new sentence in the middle that says the investment mandate requires that real purchasing power be maintained. We'll get to that in the double check with what I mean by that. So we're going to draw the TVM wallet again. I should have underlined I in the last one, but that's okay. We should know what we're dealing with if we're dealing with a perpetuity. One, two, there's the abridged symbol, and there's this symbol for infinity. $50,000. We're trying to solve for the present value of an ordinary perpetuity, so I'll put OP in parentheses. Again, this is what we're solving for, so we're going to circle that. The first payment, or the first distribution, is $50,000. The second distribution is $51,500. And I'm just going to put a ... out here because who knows how large this payment is going to get. Why is the second payment $51,500 when the first payment is $50,000? Because this payment is growing at a constant rate of 3%. Now remember, from the building block present value of an ordinary perpetuity equation, that in the denominator we have an I that is underlined, and that stands for I minus G, where I is the true investment yield that we've always worked with, and G is the constant growth rate if applicable. Well, here it is applicable, and this is what it looks like. We've got a 4% true annual investment yield, and we're told that the growth rate here is 3%. So I, and we can call this I underlined. We're still telling time with an annual period, so we'll subscript N. We know that only a true annual investment yield will work. In this case, there's an adaptation, and it's 1% in this example because we are dealing with lowercase I underlined, which is, again, the true investment yield minus the constant growth rate, because that applies here, the constant growth rate of 3%. 0 is the value for future value. There's no lump sum in the future that we're working with. We've got a perpetuity, an annuity on steroids. But there's another thing that I want to point out. In addition to 9999 being the input for N, here we input $50,000 for the PMT payment. In other words, we input the first payment in the series. And when we solve for the present value of this ordinary perpetuity, we get $5 million. That's a lot different, isn't it? That's a bigger number. It was already big at $1,250,000, but now that's $5 million. And I want to double check this math, but I also want to show you what we mean by maintaining purchasing power. So the first thing that we're going to do is we're going to double check this with the math. The building block present value of an ordinary perpetuity equation equals PMT payment over I underlined. again, where I underlined is equal to the true investment yield minus the constant growth rate if applicable. We're telling time here with an annual time span. And we know that the PMT payment, the first in the series, is $50,000. I underlined in this case is 4% minus 3%, because 3% is the constant growth rate of those PMT payments. That works out to 1%. So we can solve for the present value of an ordinary perpetuity. It's $5 million. So there we go. It's a big number. I'm going to erase this, and I want to show you, this is a little bit of bonus material here, but I want to show you how this works. Again, what do we mean by maintaining purchasing power? So I'm going to draw a timeline. I'll give myself some room here. It's going to go all the way out to infinity. Again, this is going to be a really large payment. And we just worked out the math. So it's going to take $5 million to fund this endowment. I think the action takes place below the timeline, as I'll discuss in a future lesson, but I want you to pretend that you were instrumental in helping your friend figure this out. And your friend got to the point where they made this initial contribution. And there's an investment account out there with $5 million in it. So how is that going to grow over the course of a year? These are what I call indifferent lines. And this is nothing more than the building block future value equation working for us. So this is going to grow at 4%. That's 1 plus I, the true investment yield. We're going to raise that to the power of 1. Why? Because we want to get one period into the future. So what does that grow to? It's expected that that $5 million investment at time period 0 is going to grow to $5,200,000 a year from now. Well, remember that first distribution? It's $50,000. So then the first distribution is going to be made, and the fund will, it's expected that the fund will have $5,150,000 after that first distribution is made. The growth rate, the constant growth rate in this example, is assumed to be equal to the rate of inflation. So how do we interpret this? Well, now we could use the building block present value equation to figure out what $5,150,000 will buy you a year from now. And we could divide this by 1 plus 0.03. That's the decimal form of 3%. We don't need to raise it to the first, but I guess we could if we wanted to. And when we divide $5.15 million by 1.03, that's 1 plus G in this example, which is equal to the growth rate of inflation, we get $5 million. No surprise. So how do we interpret this? $5,150,000 1 year from now will buy you what $5 million buys you today. So let's erase some of this and let's move on. We're going to use our indifferent lines again. Again, times 1.04. We can raise that to the power of 1. Again, what are we talking about here? Well, a year from now, you expect that you're going to have $5,150,000 working for this endowment. And the endowment is expected to earn a true annual investment yield of 4%. So over the course of that second year, the monies are expected to grow to 5 million. I'll put equal signs here. $5,356,000. You remember that second distribution amount? because the PMT payment is growing at a constant rate, that second amount was $51,500. Remember, that PMT payment is growing at a constant rate of 3%, a constant rate that is equal to the expected rate of inflation. And once we net this out, we're left with $5,304,500. Okay, now we're going to use the building block present value equation once again. This time we're going to divide that amount by 1.03. That's 1 plus G, or 1 plus the growth rate of inflation in this example, and we're going to raise that to the power of 2. And so here's what we're doing right here. I'm circling what we're working with right there. And when we do that, guess what we get? $5 million. How do we interpret this? Well, 2 years from now, $5,304,500 is the new $5 million. So that's what it's expected that it would take to buy $5 million worth of today's goods and services. So hopefully that was helpful. Consider that the bonus material. So that's a wrap. If you like what you learned in this lesson, please consider telling your friends about this channel, TVM Rules, and the book that made it possible. When I was writing the manuscript that later became the book, Would Your Boomerang Return, I put myself in the shoes of someone who had never before been introduced to the time value of money. And I asked myself the question, how would I like to have learned about the mathematics of finance? Not only do I believe that we've been successful, but we've also come up with some fun new takes. One of which is the Pop Open the Back Cover quiz that you can find in the book. The real world question in this lesson was an adaptation of one of the 3 questions in that short pop quiz, which can be used to gauge one's ability to apply the mathematics of finance to analyze and evaluate real world time value of money situations. You can test your TVM knowledge and see the pop quiz questions and answers on our website at boxhomepress.com. If you haven't purchased your copy yet, all the important information on this all-important topic is gift-wrapped within the cover of Would Your Boomerang Return. Until next time, enjoy the gift that is the present.